parallel sessions. And it was supposed to start from 4:45, but since we were running late with the thesis session, so there was a request from the scientific organizing committee to start it at 5, but we have a tight schedule because we have the WGG session at 6:30, and everybody is encouraged to join that session. So we have to be in time. So we have 5 speakers today. So we have first we have an invited talk from Dhiraj Kumar Hazra, who's from IMSC, and he's going to talk about one spectrum to cure them all. So Dhiraj, we will keep like 25 minutes for the talk and 5 minutes for question. And I just have one request. Sorry if that sounds rude, that I request the audience and the speaker to keep both the questions and the answers as precise as possible. Sometimes that's not possible. And I'll give you a warning, so around like 20 minutes. Is that okay? Or 23 minutes? 2 minutes? Okay, 2 minutes before.
20 minutes is fine with me. 20 minutes.
Okay, great. So I'll give you a reminder around 20 minutes, okay?
Thank you.
So, thank you so much. So I'm just stop sharing. So I now invite Dhiraj Kumar Hazra to tell us about the exciting things that's going to talk today.
Thank you, Professor Chatterjee. Okay, let me share my screen. Is this visible?
Yes, that's visible.
Okay, let me make it full screen. Is it fine? Is it coming as a full screen?
Yes, that's right.
Perfect. Thank you very much. Let me start with thanking the organizers for inviting me to give this talk. I'm going to talk about a recent work that I have finished with my collaborators. Actually, I'll be talking about 2 works that constitutes this one spectrum series of papers. And there are certain works that are ongoing as well. So without delaying, let me start. Okay, so in order to understand that one spectrum, let me start with this standard model of cosmology. What do we mean by the standard model of cosmology, right? So the standard model of cosmology is based on a few assumptions and a few observational notions, let's say. So firstly, we talk about Einstein's theory of gravity. We will not talk about modified gravity. So that is one pillar of the standard model. Metric, the way we measure distances in the universe, we call it a Friedman-Robertson-Walker universe, and that is the metric that we are going to use. And we also assume that our universe is homogeneous and isotropic at large scales. This is also coming from observations. As you know, at large scales, if you calculate the number of galaxies of the order of 100 megaparsec or something like that, at those scales, those scales or beyond that scale, the universe appears nearly homogeneous and isotropic. Okay, that's the order of the large scales that I'm talking about. The constituents, we know that the universe is constituted with baryons, but there are certain other observational notions, as I was saying, that suggest that universe cannot be just explained with baryons. You need cold dark matter, a dark matter which is not interacting with any other particles, but just interacts with gravity. It just has gravitational interaction. Of course, there can be other interaction. We haven't been able to discover that yet. A dark energy that is described with cosmological constant, okay, which has a equation of state of W equal to -1. And the initial condition, this is something new. New means this has come in the last 20 to 30 years. We came to know more about it. Is the initial condition is obtained by a complete slow roll inflation with a power law form of primordial power spectrum. Whenever I'm saying as the standard model of cosmology, it is a little bit different from the standard model of particle physics. Okay, so in cosmology, the standard model, the word standard changes. For example, earlier there used to be a standard Big Bang theory of cosmology, but then we knew that there were problems in the standard Big Bang model, so we had this horizon problem, monopole problem, etc. So we had to introduce this inflation, a brief period of accelerated expansion, nearly exponential expansion, and that came as a standard. Okay, and we have been able to know about the amplitude and the tilt of the power spectrum that you can obtain from the inflation. Okay, so these two things, the lambda CDM, which I was, okay, let me just get a pointer. So this lambda and CDM that represents the constituents, that is the model plus the primordial power spectrum assumption of the assumption of the primordial power spectrum to be power law. These two makes a baseline. Okay, that these two makes a baseline model. Also, there are a few other assumptions. For example, the neutrino mass is 0.06 electron volt, etc. The number of relativistic species is 3.046 or something like that. So that makes a baseline of cosmology. So far, the baseline is consistent with the data. So if this is the baseline or this is the standard model picture, how can we determine the standard model parameters? So we have observations, right? We have the theory, we solve the theory, match it with the observations, and we know about the parameters of that theory. Okay, so for the standard model theory, as I said, this standard model is largely consistent with the data. So at high redshifts, when we try to probe early universe, we have high redshift data from the cosmic microwave background. So for example, we had several space missions. We also have several ground-based CMB observations that gives us a very accurate picture of the early universe. At the same time, the evolution of the universe as well. Low redshifts, we have supernova, galaxy clustering, lensing, intergalactic medium, and 21 centimeter, lots of other data sets. Okay, so using all these kind of things, we can have a clear picture of our universe. But that is a modulo the assumption of the model, okay, the standard model. So what are the problems with that model? As I said, it is largely consistent with the observational picture that we get. So firstly, if we look at the CMB, we find that there are certain anomalies. Okay, when the CMB is coming towards us, there are structures that lenses the CMB photons, cosmic microwave background photons. So a photon that was supposed to be coming from the n direction goes mapped to an n prime direction, and that is called lensing. So that smears the acoustic peaks in the cosmic microwave background. This is like this. Okay, it smears. Now, Einstein's gravity, as I said in the standard model, the Einstein's gravity shows that there is a particular prediction of the lensing that comes without a parameter. Okay, and it can be derived exactly, and that comes with this parameter a lens equal to 1. Okay, so in the standard model, there is no parameter for lensing. But in order to check the consistency, when Planck tried to vary this lensing parameter, okay, it finds that the lensing parameter is not consistent with 1 at 3 sigma level. So what happens? Basically, it says that our acoustic peaks are more smooth compared to what you can predict from the general theory of relativity. Okay. So how you can solve that? So there is a solution that was proposed in the Planck paper as well, and also by in this paper, Di Valentino et al. In 2019, which says that if the universe is curved, it has a spatial curvature, it solves the lensing problem. As you can see, these are correlated. Okay, so if your universe has a omega k curvature density negative, then a lens becomes consistent to 1. Okay, which becomes, so your standard model assumption becomes true. But at the same time, your universe becomes curved. But if the universe is flat, if it is 0, then a lens has to be more than 1. Okay, you can see that this is the, so, and this is the 3 sigma tension. One actually solves the other tension. But is this a solution? Now, let me come back to the other picture. One picture was an anomaly within a data. Now there are tensions between different data sets. So there can be early universe probes, indirect detection of parameters, and late time probe where you can have direct detection. For example, Hubble parameter, this is something we all relate to. That is one of the most important parameter in our universe that signifies the expansion rate, right? A dot by A today. So the Hubble parameter, if we try to constrain that using cosmic microwave background, we get a very precise constraint, or very unprecedented. We can, with Planck last year data, we have been able to constrain it with an unprecedented accuracy, which is nearly 67 plus minus 0.5. So this is the value. However, if you look at the local measurements of the Hubble parameter, you see that they are in tension with the value that we obtain from the indirect measurements. Okay, and mostly all the local measurements go for a higher value of H0, while CMB goes for a lower value of H0. Okay, that is the story. People have been talking about new physics. Okay, and talk about a few new physics here. And there is another parameter which is called another tension, which is called S8 tension. Okay, so what is S8? And which is a combined parameter of matter and sigma-8. Sigma-8 is the root mean square fluctuation at 8 megaparsec, and that you can constrain from CMB. And from CMB, the constraint is very small, as you can see. And these are the constraints from the large scale structure. You can get galaxy clustering and weak lensing and join them. You find that this is the constraint from the large scale structure. So this is from KIDS, kilo degree survey. Okay, and this combined parameter S8, it is also shown to be 3 sigma inconsistent with the observation. So what we have now, we have anomalies and we have tensions. Okay, now, as I said in the last slide, that curvature or spatial curvature solves the anomaly of the lensing. Okay, now what happens if we take the spatial curvature? If we take the spatial curvature, if the universe is a closed universe, not flat one, look at the value of H0. It becomes nearly 50. Okay, but the problem was already that even at 67 for the standard model value, we were in a huge tension with the local measurements. All right, so spatial curvature aggravates that tension. At the same time, when you go for the omega matter and sigma 8, that tension again further aggravates. So this was the tension. This tension becomes like this. A 3 sigma becomes 5 sigma or more. I think it is 5.8 sigma or something like that. So a closed universe cannot be a solution. At the same time, you have a problem with initial condition. You try to inflate the universe, the initial condition, as I said, the scalar field drives the inflation. You try to drive a scalar field in a curved universe. You will not be able to make the scalar field roll slowly unless you make it extremely fine-tuned. So that there is another problem. So curved universe is not a solution. Separately, the people have tried for the solution of H0 anomalies as well. Anomalies people have tried with neutrino, but again, polarization data doesn't support that. So that neutrino mass has become that solution become obsolete. People have tried with a number of effective relativistic species as well. Anyway, none of them work very well. For H0, people have tried different solutions. 2 of them are very, very famous. One is the early dark energy. People are working on that with Atacama Cosmology Telescope and various other data sets as well with Planck, etc. But they solve the H0 problem only. Okay. Emergent dark energy. Okay. People have been working on this as well since 2019. There are scalar tensor theories, early modified gravity, other extension to standard model. People also have said that, well, there can be systematics in the H0 measurements as well, systematics in the Planck CMB data as well. There has been various works on those. Now, what I am trying to say is that, can there be a common solution? So in that way, what we try to do is that we try to reconstruct a primordial power spectrum that mimics lensing. That extra lensing, that excess lensing, that can be mimicked by that primordial power spectrum. We also try to see whether that power spectrum can prefer a flat universe, a spectrum that prefers higher H0 than the baseline and a spectrum that prefers lower S8 than the baseline. Okay, so we tried our method, modified Richardson-Lucy, and I think Rajorshi is going to talk about this method in the last talk. And what we find is something we called one spectrum. Okay, so this is the picture of the one spectrum. So as you can see that this is the standard model, the power law in gray, but these are the new physics signatures that we are finding as one spectrum. So let's see what one spectrum does. If you use one spectrum, which is the reconstruction, as I say, we are saying, you see that the standard model plus a lens means the lensing amplitude, which prefers a higher lensing. If you use the reconstruction, it prefers a lensing that is consistent to the general theory of relativity prediction. At the same time, it is not just making it consistent. At the same time, it is fitting the data much better than the standard model. So this is the chi-square. That it is not just one particular parameter, the chi-square. It is the whole distribution of the chi-square when you fit to the data. It is coming from the full Markov chain Monte Carlo analysis, a Bayesian analysis. So the distribution of the chi-square for the standard model is given in the gray line. The distribution of lensing, the anomaly, is given in the red line. What we are showing is that it is completely mimicking the lensing, but it is not anomalous. It is not anomalous anymore because it is consistent with the general theory of relativity prediction, right? So the reconstruction, simple reconstruction or simple reconstruction with lensing as well, both actually mimic the on standard model plus lensing with a much better improvement to the data compared to the standard model or the baseline. Similarly, the second condition was whether it prefers a flat universe, omega k equal to 0. That happens. You are seeing that this is the omega k probability distribution function, posterior distribution. If you use our one spectrum, the blue line, it becomes consistent with 0. Same story repeats here as well. We find that it basically makes the fit to the data much better than the standard model. All right. Now, this is what we showed you in the, what I showed you in the few slides before, right? This is the picture of the cosmic discordance, that this 0 line, flat universe with aliens equal to 1, the standard model predictions are not consistent. So let's see what happens when you use one spectrum. So this is what we had. If we have one spectrum, this contour simply shifts downwards. So the 0 line becomes consistent with the 1 sigma. All right, the standard model becomes consistent with 1 sigma. At the same time, our third aim, that H naught tension, that you see that when you use reconstruction, the H naught becomes higher than the standard model, which is given in gray. So there is a clear shift in the value of H naught when you use the one spectrum. So it reduces the H naught tension. It doesn't completely solve, but it reduces the H naught tension. It solves the S8 problem. All right. This is what I showed you, right? If you use standard model plus omega k, the curvature, the tension aggravates, but if you use the reconstruction, it becomes consistent to the values measured by the large scale structure observations. At the same time, the S8 parameter, the one-dimensional likelihood that you are seeing. So these are the bounds from the yellow band is from KIDS 1000. And what you are seeing here is that the green line is falling on top of that. The green distribution function is becoming consistent with the yellow band. So we are solving the S8 problem at the same time. By the way, these are the work with Planck temperature data only, because that is where the main problem lies. Okay, and that is the most precise data for the cosmic microwave background that we have achieved till now. Okay, and that is cosmic variance limited as well. Okay, now the question is that you will definitely ask, can we parameterize a spectrum? This is a numerical spectrum. Can we parameterize? So we try to do that as well. This is the form that we could parameterize with. We call it new spectrum. Okay, so new spectrum is parameterized as this. This is the baseline power law. So we have a modification with alpha 1. This is the oscillations that we impose. This is a decay profile of the oscillation, 1 plus beta times k to the 4. And this is the asymmetry that we impose as well. You can see that the asymmetry lies here, that your peaks are more pronounced than the troughs. Again, we try to do Bayesian analysis. We find that the new spectrum, the asymmetry that I was saying is not of statistical significance, not of significant it is not statistically significant, one parameter, that is the alpha 2 parameter. So what we find is that this simple parameterization can mimic the lensing. So sinusoidal modification with a decay profile. So we showed that the solutions to the problems, anomalies, and the tensions, they are correlated. If you try to solve in this basis, if you try to solve one, you end up solving all of them, or at least in some cases, you go closer to you alleviate the tension to a certain extent. That is what is happening here. So if you have this alpha 1 parameter, amplitude of the oscillations, that is negatively correlated with a length. So if you increase that, a length becomes closer to 1. Okay, this is the a length equal to 1 line. It becomes very close. It becomes consistent to 1, the 1 sigma. Similarly, it is positively correlated with the curvature of the universe. You can see that omega k equal to 0 line is coming on top of the 1 sigma. Again, it is negatively correlated with omega matter. If you have seen the curve, it helps in reducing the omega matter tension, although we are calling it together as a S8 tension. So we are showing it here that it is negatively correlated with S8. So as I said, we wanted to increase H0 and reduce S8. S8 is reduced when alpha 1 increases. Okay. So, and what happens is that, so if you talk about H0, it is again positively correlated. So if you go for higher alpha, higher values of H0 is preferred. Okay. Higher values of H0 is preferred. That becomes more consistent with the local measurement of H0. So these are the best fit spectra that we had obtained with temperature data and temperature polarization, then Atacama Cosmology Telescope data, dark energy survey, clustering and weak lensing, baryon acoustic oscillation, supernova, and Hubble space, the HST data, RIS et al. Okay. And as you can see that these are the profiles that we have obtained. And the Bayesian evidence that we obtain here are these. So the positive value means that the model is preferred. Okay. So 2.32 is something that we have obtained here. And in most of the cases, we find nearly 99% confidence level detection of that parameter alpha 1. Okay. With respect to the standard model. It has very striking features in the large scale structure. Although we have not been able to detect yet, we will be able to do so in near future. So what it does is that this is the BAO bump, baryon acoustic oscillation bump, right? If you
5 more minutes, yeah.
Thank you. So if you calculate the number of galaxies at different scales, you will find more galaxies around 150 megaparsec. If you use our one spectrum, you will find one particular signature that is yet to be discovered. We do not know. So we find that there will be, if that is the model of the universe, if that is a new physics that is supported by the data, then there will be a little bit more galaxies than the baseline model, around 250 megaparsec, and there will be little less galaxies around 300 megaparsec. Okay. So again, these are a little bit larger scales or structures, let us say structures. So, so the correlation will have a bump and a dip. In the matter cross spectrum also, you can see this oscillations that the spectrum can introduce in the K space. Okay. Now we have obtained a reconstruction. Next, we showed that the reconstruction can be explained with a power spectrum that can come from anywhere. That can come from bouncing universe, that can come from inflation, that can come from pyrosis, cyclic universe. There can be many sources. So the third step that we have showed here in the recent paper here, that this spectrum can be explained by an inflation, a model of inflation. Okay, so this is done in collaboration with my student Akhil Antoni and Fabio Finelli and Arman. So what we did here is that we tried to parameterize the Hubble flow function. Okay, so we find a baseline. We find a baseline there, which can be mapped to the standard model, and we introduce an intermediate fast roll phase in the scalar field dynamics. This intermediate fast roll is given by this. Okay, what we find is that we find with the one spectrum, And also there has been another spectrum proposed by the Planck team in 2018 release, and they become similar. We find that our inflationary spectrum actually mimics both of them. These are for different data sets, and we find that it mimics the lensing anomaly. How? In temperature data, you can see that the improvement in feed that the lensing anomaly provides, the red line, our model of inflation follows that pretty closely. Okay, as you can see that at small scale, the match is really extraordinary. Now, in polarization, what happens? Can we break this degeneracy? Yes, we can do it in polarization. We do not have a very good data, but we can have it with the CMBS4 or Simon's Observatory as well. So we have phase differences. We have completely opposite phased oscillation in the model of inflation that we proposed and the lensing anomaly. Okay, so this we can detect. These are the error bars on the data points on basically the zero line, the baseline from the CMBS4. And what we find is that in future, we'll be able to detect or choose one of these two solutions, the red line and the blue line. Okay, and TE also, the cross correlation between temperature correlation, that will be good enough as well to break the degeneracies around this scales. Now, this is the new physics that we get from the scalar field evolution. This is the breaking of the standard slow roll hierarchy or standard slow roll assumption, that standard slow roll shows that it has to be very close to zero, but you need this type of decaying oscillation in the standard slow roll. This is the next Hubble slow roll parameter, the derivative of the first slow roll parameter. This is the Hubble parameter, the evolution of Hubble parameter, and this is the potential that you can reconstruct from here. Okay, and that is what we reconstructed, and we proposed a potential. We are working on that potential as well now. So we find strong support for an intermediate fast roll for nearly 0.5 efforts during inflation. Okay, so let me summarize now whatever we had I have been discussing for the last 15-20 minutes. Is that the main achievement of that work of one spectrum and this work is that we have been able to show that there is a basis, let's say there is a primordial pause spectrum basis, where anomalies and tensions within and between the cosmological data sets are correlated. There has been no model before which shows that if you solve one, you can solve others. Actually, early dark energy model that I cited, if you try to solve H0, the S8 problem aggravates. It makes the tension between the large scale structure even worse. So one spectrum, what we proposed, provides a common solution. We find statistically significant preference for an intermediate fast roll. If the one spectrum is coming from inflation, then there is a statistically significant preference for this intermediate fast roll during inflation as a candidate for the new physics. And in future, what is in store for us? The candidate has a strong signature in the CMB polarization, which is completely different from the lensing, and has large scale structure, and at the large scale structure at particular scales. Okay, so that can be tested soon with the upcoming data, for example, Euclid or CMBS4 and a few other data sets. The CMB can be detected with the CMBS4 or ESO, Simon's Observatory, and the large scale structure can be detected with Euclid, DAISY, or large scale LSSD, Vera Rubin Observatory as well. So with that, I would like to stop. Thank you.
Thanks a lot, Dhiraj. So time for some questions. Any question? You can either raise your hand. Yes. So, Prabhapati, can you unmute yourself?
Yeah.
Great.
Yes, I've done that. Hi, Dhiraj.
Hi, Prabha.
Nice talk. So I think I missed in the beginning, your reconstruction is using only Planck data, is it?
The reconstruction uses only Planck data. Yes.
Okay. So is it correct to conclude from your results that the Planck H0 value, so if I remember correctly in your plot, your H0 value moved towards higher values, right? With your
Yes, exactly.
So is it correct to conclude that the Planck calculation should be revised? So the error is there. Is it correct to conclude that?
Okay, no. What we are saying is that we reconstruct from the Planck data. What I was trying to say is that the assumption of the power law primordial spectrum should be revised if you add certain oscillations in a particular form that can give you a higher H naught. We have found that from our change, we have found that even a value of 70, H naught of 70 or 71 in our model from Planck temperature plus polarization data gives better than the baseline or the power law. Okay. So of course there are different more parameters in our model, etc. But again, what we find is that you do not have to change the Planck data. What you have to do is that it says that if this is the power spectrum, then it is much better than the power law, and it actually solves in different direction, basically with the large scale structure, tension with the large scale structure, tension with the H naught, the Rees et al. Value, and also Planck's internal inconsistencies. But again, it is related, as you said, that Planck data has to be revised if there is a certain anomalies in the Planck data. Anomalies means that it's certain systematics in the Planck data, then this would be the face of that systematics. That at these scales, you might want to revise that. But again, we are not talking about systematics. We are talking only about the theoretical aspects. So, yeah.
Okay, thanks.
Thank you.
Thank you. So quick question, Shantanu, can you unmute yourself? Sorry, Shantanu, you raised your hand. Can you unmute yourself?
Okay, can you hear me now? Sorry, I unmuted and then muted again, and then I couldn't unmute. Anyway.
No, we can hear you.
Yeah,
Yes.
yeah. Okay, so Dhiraj, very nice talk. So just in the first slide, right? I mean, when you presented the standard model of cosmology, I guess one thing which which is not talked about much is, I guess, the physics of reheating. But in some sense, when we try to derive when we try to make when we try to constrain inflationary models from data, or we do sort of make some sort of indirect assumption about reheating, and we have to specify how many E folds before the end of the inflation. So anyhow, so my question is this non-standard primordial power spectrum, which you find is a best fit to the data, right? So I guess what implications does it have for reheating? And also conversely, while deriving this, what have you made any assumptions about physics of reheating? Hopefully
no. The answer, very short answer is no. The only thing is that we are assuming that the pivot scale leaves 20 folds before the end of inflation. So when the inflation ends, in our case, let's say 70 folds, you have to couple it with certain standard model theories in order to make it make the universe reheated again. So, but we haven't done that. So the thing is that this. So you can choose any standard theories of reheating that you are working with. You can just put it in, couple it at the end of inflation, and it will work. So the standard thing is that we are assuming that pivot scale 0.05 megaparsec inverse is leaving 20 folds before the end of inflation.
Thanks, Dhiraj. So there is somebody from the offline, the physical participant, who has a quick question. If it can be done very quickly, we can take that question. LOC, is there someone in the audience? Okay. Yeah, I don't.
Hello.
Yeah, is there a question?
Yeah. Okay. So this is this is Shubho.
Hi.
Yeah. Okay. So if I can sort of play the devil's advocate and ask him this.
Yeah.
So when you did your one spectrum, you
Yes.
sort of made it so that it fits the lensing.
Yes.
But
Yes.
the lensing basically means you're in some sense fitting the sigmoid. So why is it a surprise that it solves the sigmoid problem?
Okay. No, for example, it was not known a priori, because you see that even when you are trying to mimic lensing with curvature, you can think that it can solve the sigmoid as well, but it doesn't happen. So these are different bases. So this is threefold degeneracy. One part is the lensing. Second part, which Planck and Eleonora showed, that the curvature. These two selects completely different sets of cosmological parameters. So curvature selects a S8, which is much higher. However, and also H0, which is much smaller, 50. So we did not know a priori that this is going to solve, for example, but we knew that it is going to solve the H0 to a certain extent, because A lens goes for higher H0, and we use that H0 values in order to reconstruct. Okay, and we also did a reconstruction using the HST data earlier, which showed very similar curve, but at that time it was so noisy, the reconstruction was so noisy, we could not see the underlying picture. But here, with the new method, we have been able to show that it can be done with a simple power spectrum. Yes, so in some sense, certain things where we could anticipate, but not all of them. Like S8 can be reduced when you use that power spectrum. As I said, curvature could not do that, right? That also mimics lensing. So this is the third part of the degeneracy, which is consistent with all the others, but at the same time, it is physical. The lensing is not actually, sorry, A lens or the excess lensing that is unphysical. This problem we do not have in our model.
Okay, thanks a lot, Dhiraj. So our next speaker is who asked the question, Subhabrata Majumdar from TIFR, and he's going to tell us about non-thermal SC, cosmology and astrophysics with the new kind of secondary CMB anisotropy. So Shubho, so for the contributed speakers, we have 12 minutes and 3 minutes for question. So after 10 minutes, I'll give you a reminder. Okay?
Okay.
Thank you. Yours is in-person talk, right? Yeah.
That's right. Can you hear me?
Yes, yes, yes. Thank you. Please start. Yeah.
Can I start? Yeah. Okay. So, okay. Thanks, everyone. So this talk is mainly aimed about the sort of the demography that I see happening with ASI meetings, more and more young students and young postdocs, which is really good. From the time that I used to go there as a student, where very few students used to go. But so that basically means this talk is less technical than it can be. So please ask questions after this 15 minutes if you have. So I'll be happy to answer them. So today I'm going to talk about something very, very new, which is non-thermal SZ, Sunyaev-Zeldovich effect. I'm not even sure that you have heard, all of you have heard about Sunyaev-Zeldovich effect. I don't have time to do that, but I will try to say a little bit about it, okay? And what kind of new things we can do with this non-thermal Sunyaev-Zeldovich effect, okay? So Dhiraj in the last talk had been focusing on CMB, and when he talks about CMB, what he mainly focuses on is what is known as the primary anisotropies of the cosmic microwave background. So, you know, when you look at the CMB sky, we get the anisotropies from the cosmic microwave background in the cosmic microwave, the spatial anisotropies, and they are mainly due to the photons having those anisotropies imprinted on them at the last scattering surface, which has a redshift of 1,000 or so. But those photons come to us, and while they come to us, they gather new anisotropies. These new anisotropies are distinct from the primary anisotropies that Dhiraj was talking about, and these are called the secondary anisotropies of the cosmic microwave background. Now, there are things that make these two anisotropies different. One prime thing is the scale, the spatial scale in which these anisotropies are. So if you look at these four figures over here, if you look at the top right corner, over there, what you see is only the primary CMB anisotropy. So if you look at, so don't look at me, look at the screen. So if you look at the screen, you will see that you see these hot and cold spots of the primary CMB anisotropies. Now, hidden in it are also the secondary CMB anisotropies, but we cannot see it. Now, when I take this top right-hand corner and filter it with 4 arc-minute, you still cannot see the secondary anisotropies. But you make the filter even smaller, 2 arc-minute, so which is the left-hand side, bottom left side, you can see some spots that is appearing, okay? And then if you make the scale even smaller, then you see all these dots that you have come up. These dots were hidden over there, but they were there in the first plot on the top right. So these are the secondary CMB anisotropies. These are the ones that the CMB photons have picked up as they traveled from the last scattering surface to us. Now, if we can study these anisotropies, then what we are getting is a huge amount of information about the entire universe for the last 14 billion years, a redshift of 1,000 to us. The formation of the structures, how they form, what are the energetics, everything is imprinted on those spots. Okay. So if we now look at the power spectrum, so the amplitude of fluctuation about lines going through the spots or the correlation, then those will give us extra information. To show it in the terms of the future, you see in the future, there are three main goals of CMB studies. One, which is the primordial V mode, you must have heard of. Then there is something called the early universe spectral distortions. And the third is this secondary CMB anisotropy. So today I'm going to talk about the third part and something new about it. Okay, so this is the CMB power spectrum that you have seen many, many times. And this is what started precision cosmology. And this is what Dhiraj was talking about, this standard model of cosmology, which is sort of been foundation and has been on this CMB primary anisotropies. But if you look at the experiments that went from Kobe, WMAP to Planck, these are the major experiments. And at present, there are, I would say, not that many major experiments planned, which will be focusing on primary CMB anisotropies. Okay, so as you can see, as this wiggles and bumps and it falls, as we go to higher L values, so there are small angular scales. Angular scales are inverse of L values. Okay, this is where the secondary anisotropy starts. The one which is the most famous is known as the Sunyaev-Zeldovich effect from clusters of galaxies. So this is the blue line that you can see, which is the dashed, the thermal SZ effect. This is where the CMB photons, when they pass through clusters of galaxies, the hot gas in the clusters, they give energy to these photons and the spectrum is distorted. So the clusters of galaxies, if you look at the cluster of galaxy, they will look as a dip in the microwave background at lower frequencies and a hot spot at higher frequencies. Okay, so you can see them. So that is one. Then there is something called the kinetic SZ. Now, one thing that you should understand over here, and I don't have time, is that the way people try to find these anisotropies from the primary is by the spectral feature. So you know the primary anisotropy is a black body. It has a black body spectrum. The secondary anisotropies do not have they have almost black body. They have a slight distortion. And you know the exact frequency dependence. So in knowing the frequency dependence, I can find out the blue line from the red line on the top, although you see that by amplitude, the blue line is so small. So it turns out that at certain frequencies, I can, by canceling maps, I can get rid of the red line and only the blue line remains. Okay, so by frequency dependence. It also turns out the green line, dashed line, which is the lowest of them, it has the same frequency dependence as the red line. So it has a lot of physics, but it's difficult to disentangle them. So then one has to think of spatial dependence. Remember last time I showed you that by looking spatially, you can look at the spots. So these are spatial correlations. So find it in space. Okay. So these are two things. So two different kinds of secondary anisotropies. But there are more. For example, I can think of reionization. And reionization gives you another dashed dot line that I can see over here, which is from the one kind of reionization. Then there's some other kind of reionization that will give you another lines. Again, these are sort of the same frequency dependence as the primary anisotropy. So it's difficult to do it in frequency domain, but has to be done in spatial domain. So one has to look at spatially and see and do some spatial filtering to get it out. One can have more. So as you can see, there are many secondary anisotropies. For example, this pink dots, these are not from clusters of galaxies. These are hot winds coming out from galaxies. And they have, again, a different kind of frequency dependence, different kind of clustering. But what I'm going to talk today is this dotted line that you can see, this thick dot line that you can see, which is much smaller than all of these. It has a unique spectral dependence, which is known as non-thermal secondary CMB spectral dependence. And I will show you why it is unique. Okay, so this has a spectrum which is different from all of these. And so one can take this out if I have a multi-frequency experiment. And so even though it is so small, one in principle can detect it. Okay, so where can we find this kind of objects that will have this non-thermal CMB? Something that you have seen, a lot of you have seen, is radio galaxies. So in the right-hand side is a classic picture for radio galaxy. You can see a radio jet. There's a center, and then there's two jets coming out. There are two hot spots on the two sides. And a physical model of that is on the left-hand side, the schematic. Now, what you can see that the hot spots over here that you see bright on the picture are the two dark circles on the right and left-hand side of the schematic. And in the middle of the picture, everything that you see within the ellipse is basically a region which is filled with non-thermal plasma that has been ejected by this radio galaxy. So think of it like a water pipe, hose pipe. That is, this plasma is like a hose pipe. It is, going on the wall, and when it hits the wall is the intergalactic medium. It sort of, as the water comes back, it sort of comes back to you. And think of the wall as if the wall is on wheels. So the hose pipe hits on the wall moves because it's on wheels, and the plasma has some pressure. But the thing is becoming bigger and bigger and bigger, and it's filling up the region because the water comes back to us. And so you get these huge regions, elliptical over here, which is filled with non-thermal plasma, and these regions become bigger and bigger. It turns out that although this is so messy, we can actually have a model in simulations and also in theory in which we can really calculate how the density of this plasma grows with time, what happens, how the sizes increase. And so this is exactly what we have done. I'm not sure any of the details. And so, for example, I can look at a radio galaxy and I can calculate 5 minutes.
2 minutes, actually 10 minutes it has been.
Yeah. So I can look at the radio galaxy, I can look at the power and the size of the cocoon, or the size of plasma and things like that. Okay. So we know how to calculate the properties of plasma. Once we know how to calculate the properties of plasma, we can calculate how much CMB distortion each of these radio galaxy gives as a size of the plasma of the cocoon. So this is what is plotted over here. I don't have time to explain. What is interesting is that, as I told you, these plasma, this non-thermal, has a frequency dependence, which is very different from others. For example, over here on the left-hand side, if you can see the light green plot, that is the frequency spectrum of the thermal SZ effect. And the others are the frequency spectrum of this non-thermal SZ effect. Okay. And so this is different, and one can find out with this. One can sort of extract this different kind of effect. And in future, we can do that. So what do we have? What we have, why this thing was done, was the first SZ observation of such a radio galaxy in this CMB was done very recently, like 2-3 years back by Malu et al. And if you look at the right-hand figure, the two green spots are the two lobes of the radio galaxies that you are seeing in CMB. So now, till now, for last 50 years, people have been looking at radio galaxy in radio. Now we have seen it in CMB also. So now we have radio galaxies both in CMB and in radio. And once we have that, we can basically fix the model that we have of radio galaxies. The models had free parameters, and they're completely fixed by these two observations. And so now we have a fixed model, which is over here, radio on the y-axis, CMB on the x-axis, and every model must sort of be at the juncture of where the observations are. And then what we can do is that we can find out how much of this distortion of the CMB comes from radio galaxies. And for the experts over here, the interesting 3 lines to look at are the heavy lines that I've drawn. The blue line or the purple line is that from radio galaxies, whereas the red line is the much awaited mu distortion from primary CMB. As you can see, the radio galaxy distortion is well above the mu distortion. So if you have to look for this holy grail of mu distortion, you need to look at radio galaxies. And these are the sort of pixie and super pixie kind of errors. One can also look at what is the power spectrum. You can see that's like 10% of the SZ power spectrum. What I want to show very quickly in 1 minute is one very interesting thing that we can do now. So let me tell this idea. So one of the ways to do Hubble constant is to do distance ladder independent Hubble constant by doing what is known as Hubble constant from clusters of galaxies. That's one way of looking at Hubble constant, looking at clusters of galaxies in both SZ and X-ray, and get a Hubble constant without any distance ladder. So ask me what is distance ladder later. And this has been the way to do Hubble constant for the last from 1978 onwards till now. And there has been no other methods. The radio galaxies now give us a unique way to do this. For example, now, if I know for one radio galaxy, the observed YNT and the observed radio power, then I know exactly the position where it meets. And if I know the redshift of the radio galaxy, that gives me exactly the distance to that radio galaxy. And so what we have is, this is from clusters of galaxies, what people have done over last 30 years. And with one radio galaxy that Malu et al. Discovered, we can put it over here. Okay. So what?
So time's up. Yeah.
Yeah. Last. So what we see is that all the Hubble constant measurements, for example, a new way of this distance science with this green one line, and this one Malu galaxy gives you a new red colored one, the new Hubble constant for radio galaxy. So it's opened up a completely new way of doing Hubble constants. So this is where I sort of leave you with a sort of prophecy that SZ and H0 from SZ, RMS or whatever from SZ started like 50 years back, and now we are at competitive stage. We are proposing something that can be the same in 10 years' time. So the first cosmology with non-thermal is about to begin, and the first observation was already there, and the first Hubble constant measurement is already there. So this is where I will stop, and I will leave you with this old figure of secondary series. Thank you.
Okay. Thank you, Shubho. Now, maybe just because we are very, very tight in time, time is up. So maybe if there is one offline question, any physical participant wants to ask a question, we'll take that. If not, we'll move on to the next speaker. Is there somebody? Yes, please.
Yeah. So first of all, very nice talk. Can you just move to your previous slide?
Previous slide, which one?
Where you have shown the new constraint. The next one.
This one?
Next, yeah, this one.
Yeah.
So here you are showing that this red line is constraining, is a new method of constraining. But isn't this line quite a bit wide?
Yes, it is, because it's one galaxy. What was the first measurement of Hubble constant from
25
clusters?
Oh.
It was huge. I mean, always think of gravitational waves. The green line is the gravitational waves. One measurement, so promising. Look at the constraint. One source of gravitational wave. It will become smaller.
Okay,
As
so
soon as I have like 10 radio galaxies, it will become smaller. All these things are averages.
okay.
Okay, thank you very much. So we have our next speaker, Anshuman Tripathi from IIT Indore. And this will be a physical talk again. Anshuman, please start. Are you there? Yeah.
Yes, ma'am.
So I just request the speakers and the audience, the people who are asking questions, to try to be a little precise with time. Thank you. Doesn't mean to be rude, but it's just a request. Please start.
So good evening, one and all. My name is Anshuman Tripathi, and I am a second year PhD research scholar in the Department of Astronomy, Astrophysics, and Space Engineering at IIT. And today in this talk, I am going to talk about the extracting the H121 centimeter signal from the low frequency observation, radio observation, using the artificial neural network. It is covering the slides. Yeah. So during this talk, I will cover these following topics which I mentioned here. So let us begin with this picture. So this picture nicely shows the evolution history of the universe from its very beginning time when the Big Bang happened and to the till present day. And I have mentioned all the important timeline of the universe, like the recombination era and the cosmic dawn and reionization with corresponding redshift range here. So, so in 21 centimeter cosmology, the observable quantity we measure in terms of the fluctuation of the brightness temperature delta TV, and this delta TV measures the between the spin temperature and the CMB temperature. And to measure this quantity, there are various experiments going on, in which some are based on the ground-based observation, and some are based on the sky or like space-based observation. So, in which the some of the experiment they are actually based on the single radiometer technique, and they target to measure the signal as in terms of the sky average signal, or we call it as the global signal. So I have mentioned the experiment, some of the experiment name here, and in another technique where we use radio interferometer technique. Here we use multiple dishes at a time, and here we observe the signal in terms of the power spectrum and tomography of the IGM. So I mentioned the experiment name here in my slide, so you can read this thing. So as we know, our signal is very much faint. So it is obvious it will be there will be observational challenges. So the first observational challenge is the high amplitude foreground, which is 10 to the power 4 order higher than the signal. And another challenge is the Earth ionosphere. The Earth ionosphere also distorts this cosmological signal significantly, and it introduces the directional dependent effect. So basically, I will discuss this ionospheric effect in detail in my upcoming slide. And there are another effect also, like the beam chromaticity effect, the radio frequency interference, and the other systematic effect, which also distort this cosmological signal significantly. And in upcoming years, the huge data size is also going to be a big challenge for the astronomers. So in my work, actually, I use artificial neural network to stack the global 21 centimeter signal parameters along with the foreground and ionospheric parameter from the composite all sky average global signal with including the foreground and ionospheric effect. So before going to detail of my work, I will like to discuss some basic detail about the artificial neural network. So the artificial neural network basically inspired by the biological neural network, and the basic structure of the artificial neural network consists 3 layers. And the first layer here we call as the input layer, and in the input layer we have given to the input to the model. And the another layer we call as the hidden layer, and it can be more than one. It totally depends upon our problem complexity. And the last layer where we received our result, we call it as the output layer. And the ANN, like the training procedure based on the 2 algorithms. So first algorithm is the feed forward process, and the second algorithm is the back propagation. So because of the time constraint, I'm not going to detail about this. So once our model has been trained, validated and tested. So to check our model performance, we calculate the RMSC score and R2 score. So by using this, we can see that if the RMSC score is like near to 0, so we can say that our model evaluated good. Or if the R2 score is near to 1, so we can say that our model performance is well. So, so in my work, I have used the acceleration reionization era simulation code to produce the global 21 centimeter signal. And this model, actually taken the parameters, basically three parameters, which is JZ, Lyman alpha background, and in this parameter determine the strength of the Wilson field coupling. And the another second parameters given to the model is the ionization fraction of the hydrogen. And the third parameter we given to the model as a temperature of the intergalactic medium. And these three parameters, they evolved as the 10 hyperbolic function. So, and to model the foreground, I have used log polynomial foreground model. And here actually, I have used reference frequency around 80 megahertz. And for our work, actually, I have restricted this foreground model to till 3rd order only. And the corresponding parameters for that are A0, A1, A2, and A3. Yeah, and to model the ionospheric effect, basically, I have divided the Earth ionospheric into 3 layers. And the first layer we called as the D layer, which is the lowest layer of the ionosphere. And the topmost layer we call as the composite F layer. And in between there is E layer. So in the F layer, basically the electron density has higher. Electron density region are higher. And outside of this F layer, the density is completely lower. So if any electromagnetic wave passing through this F layer, it got reflected on the boundary. And because of its spherical shape, it deviated toward the zenith. So any ground-based antenna which is recording the signal, so it will record the wider sky area in compared to the actual one. And because of that, it record the higher temperature in compared to the actual record. So, and in the D layer, the electron density is not higher in compared to the F layer, but it has high density atmospheric gas, and because of that, it absorbs the signal and it emit as the thermal emission. So I just calculated the deviation angle by using this, the given formula, and I have just plotted this effect for the mid-latitude electron column density around 10 TeXU, and here you can see that the deviation angle is increasing when the frequency is decreasing. So, and similarly, we can also see that the field of view is also increases with respect to frequency. And for this, the D layer effect, when we have plotted the attenuation coefficient with respect to thermal emission, so we can see the same effect. Like when the frequency is lower, so the effect is higher. So we can see that the ionospheric effect is higher when the frequency is the lower in compared to. So when we move into the higher frequency range, so the ionospheric effect got it is less in compared to the. So I just calculated all these effect by using, so the final antenna temperature, I just calculated this T ion antenna formula. So now to train our model, I just constructed the training dataset by varying the parameters for the signal by 50% plus win. And I just consider the two cases when we add the foreground only, and when we add the foreground and anisotropy effect. So when we add the foreground, so at that time we have total 11 parameters. And when we consider the ionospheric effect, so at that time the total number of parameters we have 30, because the ionospheric effect also introducing two more parameters, which is sec and T. So
you have 2 more minutes.
Okay. So once our model, once our training data set is constructed, so we just divide this training data set into 3 portions for the training for the model, and to validate our model and evaluate the model. And in the test data set, I have added the thermal noise, which is by following the radiometer equation. And this radiometer equation, basically, the variable parameter is the observational time. So this is the flow chart of the work. So what we use. So once our model is trained, so I just tested our model from the first case with the 180 sample of the data set, and with corresponding thermal noise of the 100-hour observation time. And here you can see that our model predicted the parameters with the 97% accuracy for all the in the signal and for the foreground. And for the second case, when we add the ionospheric parameter effect also, so we also we tested the train model with the 180 sample test data set, the corresponding observation hour 1000, and here you can see that our model is predicted the parameter with the 96% to 97%, sorry, not 98% for the So to check the robustness of our model, I have used another kind of data set which have high amplitude signal, basically following this high amplitude signal basically inspired by the edges. And this data set is presented by the Madhurima Chaudhary et al. In 2018. And here the parameter set is also different than the Aries model. And I also I just applied the same thing in this data set and tried to construct the extract the parameters. So here you can see that the model predicted the parameters for the case when we consider on the foreground. So for the signal, you can see that the lowest parameter, the R2 score is the 72%, 73% around. And here we are getting the foreground parameters very well. And for the case when we consider the foreground with anisotropy effect, so here we are getting lesser in F escape parameter, and others parameters we are getting very. So in future we are planning to add time varying and anisotropy effect into our model to try to estimate the global 21 centimeter signal from there. And we also want to estimate the global 21 centimeter signal parameter by considering the chromatic primary beam effect. And in future, we try to investigate the effect of improper knowledge of the primary beam and anispheric on the section of the 21 centimeter power spectrum from the observation of the scale like.
Thank you, Anshuman. One quick online question, if there is any online participant has a question, please raise your hand.
There is an offline question.
Okay, then please, offline question, please ask it.
Hi, thanks, sir. I just was curious about your parameter estimation using VMS.
Okay.
And is it worth also checking that with some other estimation methods, like say MCMC, for example, of how different those best estimated results are compared to what you have extracted in the slide 19?
Yeah, actually, we are trying to do with the we are trying to our next approach is to build this as a emulator and try to extend the parameter using the MCMC so that we can get more aesthetics.
Okay. Thank you, Anshuman. So our next speaker is Fazlu Rahman from Indian Institute of Astrophysics, and that's also a physical talk. So Fazlu, please. Thank you. And I'll give you, after 10 minutes, I'll give you a warning. Yeah.
Hello everyone. Good afternoon. So I am Fazlu Rahman from the Institute of Astrophysics, Bangalore. So first of all, I would like to thank the organizers for giving me this opportunity to present my work on the multi-frequency statistics of galactic synchrotron emission. So most of the things that I'm going to present today is already published in JCAC. So this work is done with my supervisor Prabhapati Chimukal from IA Bangalore and my collaborator Tuhin Ghosh from NICER Bhubaneswar. So here is the outline of my talk. I'll briefly touch upon the CMB and galactic foregrounds, and I'll give some review about Minkowski functionals which we use as the statistics, and I'll briefly explain the analysis and results that we obtained from Haslan map, WMAP, and Planck synchrotron maps, and I'll conclude with discussion and conclusion. So we know that, as in the previous talks we have heard, that CMB has given us enormous information on the whole Big Bang phase as well as the evolution of the universe. But the story is not complete. The next goals are there. We have to capture inflationary denotes. Also, primordial non-gaussianity is there to be captured. Also, the spectral distortions, both primary and secondary, are there, as Shubha was speaking. So there are many goals, and what are the main challenge we have? So one of the major challenge we have is from the foreground emissions. So there are a lot of foreground sources. So mainly from from extragalactic sources as well as galactic sources. So in this talk, I would like to stress more on the galactic emissions and how significant they are. So we can divide them as synchrotron emission from a galaxy which dominate in the low frequency part of the CMB spectrum, and we have thermal dust emission at the high frequency part. Also, free emission is the spinning dust emission is the which we call as the anomalous microwave emission. So the thing is that in order to capture mainly the B-mode signals from the primordial inflation, we have to separate these emissions, this highly polarized synchrotron and dust emission, which can be seen in the right plot, where the R equal to 10 power minus 4 BP power spectrum is very small comparing to the highly emitting synchrotron and thermal dust. So the conclusion is that accurate modeling of galactic emission is crucial to capture the tiny signals from the early universe. So how do we do that? We have to understand the galactic synchrotron and thermal dust emission, which is the focus of my talk today. So galactic synchrotron emission, we know that it's a relativistic electrons and protons in the cosmic rays. When they interact with the galactic magnetic field, they emit synchrotron radiation. So all-sky map that we have right now is the best map that we have so far is the Hazra map, which is widely used in all the CMB compensation techniques, which is at 408 megahertz. But there are also all-sky maps given by WMAP and Planck, which are the derived quantities based on the compensation methods employed in these missions. So I have just shown the colorful images from Hazra map, WMAP, and Planck, both in temperature and polarization. Okay, so in this talk, I would like to focus more on the non-Gaussianity of the synchrotron emission. So we know that synchrotron emission is a highly nonlinear emission, because of which we can expect that it will be highly non-Gaussian. But while modeling the synchrotron emission, people assume that at the fluctuations of the synchrotron emission at small scales, they are Gaussian and they are statistically isotropic. So this assumption is mainly taken on the basis of the fact that it will make the calculation simple, even though we don't have any physical motivation to take this. So people have done the bispectrum skewness and kurtosis analysis using synchrotron to check the validity of this approximation, and they found that okay, if you go to small scales, it's becoming more and more Gaussian. But given the highly non
Sorry, did I lose the speaker or? Hello, is there an issue? Yeah.
For some reason, I have become host of the meeting, I think because the other person, I mean, LHC left. So should I make you the host? I think.
Yeah, you can make me the host. Yeah, if that's, but then
it might be more convenient.
Yeah, thank you so much, Dhiraj. Yeah, but this person was, this is a physical speaker. So let me call them, okay? Once, yeah. So yeah, I just called them. I think we'll be late for the piece. Can others hear me? Can people hear me?
Hi, yeah, I can hear.
Okay, thank you.
Yeah, I think
So
people are
let me
messaged
just,
actually.
yeah, just
They
a
can-
second. So I guess the local internet there is a problem. So Rajorshi, maybe it's a good idea to start your talk. Can you
Okay.
do that now? Yeah.
Okay,
So
sure.
so we just had a technical issue, and now Rajorshi Chandra, who just submitted his thesis at IUCAA, will give the presentation. And once the local internet is resumed, we'll get back to Fazlu's talk. Thank you very much for your patience.
Hi, am I okay? Yeah,
Yes,
I'm
yes.
unmuted.
Yes, you are.
Are
Your
my
slides
slides
are
visible?
Yes,
Okay,
that's right.
great. Okay, thanks. Hi, everyone. So my talk is titled Primordial Power Spectrum Reconstruction from CMB data via weak lensing perspective. And I did this work with my supervisor, Professor Sharadeep. And it's based on these two papers. So first one is published and the second one is prepared for submission. And they're both on arXiv if someone's interested. So I'll give a brief overview of this, of my talk. And the weak lensing physics, the deconvolution technique that I'll be using, and the results from the two papers. So this map is probably quite well known by now. These are the CMB temperature anisotropy. There's a CMB temperature anisotropy map obtained by Planck, and this is the corresponding 2-point correlation function of the previous map. This is the weak lensing potential map, also obtained by Planck using minimum variance estimation. And this is the 2-point correlation function of the weak lensing potential from different missions, dark blue being from Planck. And both these, so these maps in the lambda CDM model are modeled as Gaussian random fields and are considered statistically isotropic, which is why I work with the power spectrum, CLTT and CL kappa kappa or phi phi. This is a cartoon of the weak lensing process. You have the surface of large scattering, the anisotropic photons being lensed under the weak lensing regime by the intervening matter distribution until they reach observation, like our eyes today. So this is the core weak lensing math, like what are the effects of weak lensing? So you have the CLTT that I showed earlier. The lensed power spectrum becomes a function of the unlensed power spectrum convolved with the lensing potential power spectrum and some geometric factors, SA and SB, of which the functional part is the Wigner 3J symbols, which are equivalent to the Clebsch-Gordon symbols that connect the different angular modes together and mix them up. So our goal is to basically get the primordial power spectrum from this convolution. This is the observed data. This GL are the kernels that contain the rest of the lambda CDM physics, all the, the radiative transport kernel, all the other 6 parameters. And generally PK is modeled as a power law with 2 parameters, AS and S. So Professor Hazra's talk has already mentioned the motivations and the underlying work done for this for this kind of approach. So PK here is a free form variable and model independent. Each PK is a free variable effectively. Due to lensing, this kernel, which was originally just a function of the lambda CDM physics, now becomes a function of PK as well because of the previous equations, right? So now it's kind of a nonlinear convolution. Your observed lens temperature data is a nonlinear function of PK. So the first, The
We can't hear you. Yeah.
Hello.
Yes, please.
Yeah. Okay. So this is the Richardson-Lucy. I'll turn off my video. I think the internet is slowing down. Yeah. So there's a Richardson-Lucy deconvolution iterative algorithm. So you basically give it works for positive data. Your RPK, CL, these are all variances, so they're all positive, and the kernel is a square. So these are all positive data in which regime this estimator works. So you give it input guess of pki, and given your kernel and your data, you iteratively solve it to get a better and better estimate of pk, which eventually should converge. And this is an optional error weighing term in case you have errors like the sigma inverse or 1 upon sigma for your data. In our case, one of the modification we propose for a nonlinear convolution where your kernel is a function of pk is that each of your previous iteration of pk is fed back into the kernel as a correction term, this delta glk function of pk. And the assumption is that given a small nonlinear correction like for lensing, which is at max 10% of the original power at high L's, that eventually your updated pk should converge to the correct reconstruction when you're accounting for this nonlinearity iteratively. So here we just show you the lensing kernel and the temperature, the lensing potential kernel and the temperature kernel. So these basically show how the lambda CDM physics are represented in the plots visually. So now in the first project, we apply the standard Richardson-Lucy deconvolution algorithm on a power law-based synthetic data given in orange, and then we take cosmic variance limited realization of that data. So when you reconstruct the power law using the Richardson-Lucy algorithm, what you get is this. And these are the error bars from different realizations of the same data, Monte Carlo realizations. So this is the original input, and this line is the output. So you can see within the error bars, it's successful at reconstructing back the power law itself. And we also provide a sparsity algorithm that reduces the number of degrees of freedom. So you can you have a better statistical estimate of any features you might get in your reconstruction. The sparsity also helps us in getting the full covariance metrics of the reconstructed primordial power spectrum and the correlation metrics. And this can be used for chi-square validation of any features you find, or to further reduce. So you can see there is still some correlation here. So you reduce the degrees of freedom using, let's say, a principal component analysis. You can further reduce correlations and improve the validity of your reconstruction results. Now we move to the second part where your lensing causes a nonlinear addition to your temperature power spectrum. So we want to, as a proof of concept, we want to show that our iterative proposal, the correction to the Richardson-Lucy algorithm, gives better results. It gets rid of the bias or systematic due to lensing. So here now we input a PK, a primordial power spectrum, with this Gaussian bump added. It's a synthetic feature. And from that, we now construct this lensing potential power spectrum. And you can see the excess power added here and the temperature power spectrum. So you can see this is the original power law, and this is due to our synthetic feature, this dashed line and the full line, the unlensed, and each of them has a lensed and unlensed component. So the delta lensing, the effect due to lensing is plotted here, and you can see the power law is the orange one, and the feature one is the blue. So you can see how features can add or change your lensing contribution. This is the fractional difference due to the change in feature in lensing. So now when we do the reconstruction, we will do 4 types of reconstruction. One is using the original Richardson-Lucy on the unlensed data, which is the ideal case, which is given by the first plot. So you see we can reconstruct the feature very well. The second one is you take the lensed data and you apply the original Richardson-Lucy without correcting for lensing. So now, as you can see, there are these spurious features because of that excess lensing power. So this has already been addressed in literature that this issue arises earlier. And so Hazra et al. Have worked on this, and they proposed a template correction system in which they subtract a power law-based theoretical lensing template from the lensed data. So in principle, if your data is reasonably low or normal precision, this is enough, because beyond that correction, it's not really necessary. Precision can't make out that correction has been there or not. So if you do the template correction and then add the normal Richardson-Lucy, what you get is something like this. You get the feature with some, artifact still visible. But if you apply the method that we propose with the iterative kernel correction in Richardson-Lucy, which we call the NIRL, nonlinear iterative Richardson-Lucy algorithm, you get the exact, more or less close to the original unlensed data, but this is from the lensed data without assuming any power law template or anything of that sort. So at least for proof of concept, our method definitely does work in, correcting a systematic bias due to lensing or not being able to account for lensing much more accurately. So this is the relative error plot. The red is when you don't correct for lensing at all. The orange is with the template correction made, and the blue is with the iterative method that we propose. We do the exact same process all over again for the same data, but this time with cosmic variance limited error-based fluctuations added. They're basically cosmic variance error bar-based realizations. So we do the same analysis, and this time the orange is the raw reconstruction that we get. And we also bin it just to see that this, as you can see, the realization noise is also being reconstructed by Richardson-Lucy. So can your reconstructions be reliably, can they reliably separate the realization-based noise versus your features from data itself or some systematics like
So
lensing?
2 minutes, you have 2 more minutes, okay?
Right. So as you can see, so as you can see, the lensed one, the unlensed data, the ideal one gives you this plot. The lensing without correction, you can get rid of the realization noise, but you still get these artifacts surviving. Template improves it a lot, you get small amount of artifacts. And when you do the iterative one that we propose, you get the more or less close to the exact original input. And this is again the relative difference output as before, but with the realization noises. And you can see the iterative one significantly removes almost all lensing systematics. And as mentioned in Professor Hazra's talk earlier, where they proposed the one spectrum using a sign-based, feature and motivated by the parameterization, we also use that kind of feature as a synthetic input. And we show that based on the unlensed ideal, lensing uncorrected, template corrected, and are iterative, you get these reconstructions. And the relative fraction, the relative difference shows that the iterative method is again successful at removing a significant portion of the lensing systematic that the template cannot get rid of. And this is, of course, so you can see this is much more physically motivated because our observations rule out synthetic features like the bump we showed earlier, but the sign feature is quite relevant even within observations, and it's close to cosmic variance limits. So basically, so I conclude the talk here, and the summary is that the Richardson-Lucy applied on the lensing power spectrum is a good sector of new data where you can get PK independently and use it for constraining your future reconstructions. And it is also possible to iteratively debias or account for the lensing systematic without assuming any template correction, like in which you assume a power law beforehand. And a proof of concept works, and it also works for latest data-based parameterization such as the sign-based model by Hazra et al. And the cons of this method, it uses a much more amount of RAM or computation time. They're alternate, and you can select accordingly. And this method may also be useful in other sectors which have the same positive data, conditions, such as in optics, where originally actually Richardson-Lucy comes from the optical sector only. It was used for de-blurring images, etc. But this iterative correction can be used again. So yeah, thank you.
Thank you so much, Rajorshi. So one quick question.
Yeah.
If there is a quick question, please unmute yourself and ask. Otherwise, I see Fazlu Rahman, and we can ask him to continue the talk if he's available. So, any question for the speaker? Maybe a quick one. Okay. If not, just one. Can you just say one quick motivation, Rajorshi, about using your Richardson-Lucy? I see that you write here, but why would, what is even the benefit for using that? Just quickly.
The general, the Richardson-Lucy benefit or the correction that we propose to it?
The Richardson-Lucy benefit.
Okay, the Richardson-Lucy benefit is basically a model-independent way of looking for features in PK. So effectively, you're increasing the degrees of freedom. You're increasing the number of parameters. So you're better able to fit your data. You're better able to fit your data and maybe find hints of some features in PK. Because if you use, let's say, a power law which only has two parameters like AS and NS, you're constrained by that model. So either you have to keep, fitting multiple different models one after another and then do model comparison like a Bayesian, that model comparison factor, etc. But this is a good way to do a model independent approach and find features basically.
Okay, thank you very much.
Yeah.
So we'll have our last speaker. So Fazlu Rahman, who got actually cut because of the local internet issues.
Should I
Thank you
stop
so
sharing?
much. Yes,
Yeah.
thank you,
Okay.
Rajorshi.
Thank you.
So Fazlu, can you share your slides? Yeah. Fazlu Rahman, are you there? Yes.
Yeah. Hello, ma'am. I'm here.
Yes. Yes, you're audible.
Okay.
Yeah. Do you want to share your slides? Yeah. You can start
Yes.
from where
Can
you
you
stopped.
yeah. Yeah. So can you please enable me to share the screen?
Yes, I did.
Okay. You can see my screen.
Yes, yes, we can see your screen. So you can just start from where you stopped.
Can you see my screen now?
Yes, yes, we can see your screen.
Hello?
Yes,
Okay.
we can see the screen.
Yes, yes. Okay. Okay, the non-Gaussianity of the synchrotron field. So for modeling synchrotron emission for CMB experiments, it's assumed that at small scales, the fields are the fluctuations in the field are Gaussian and statistically isotropic. So it's important to check the validity of this assumption. It is taken mainly to make the calculation simple. So the main goal of this work is to check the validity of this assumption. So in this analysis, we are studying the statistics of synchrotron intensity map using Haslam map, which is the standard template for the synchrotron map, as well as the derived synchrotron maps from WMAP and Planck. So we use the morphological tools, scalar and tensor Minkowski functionals. So the main goals of this work is to carry out a detailed analysis of synchrotron maps and check the validity of approximations of Gaussianity and statistical isotropy at small scales. Also, we would like to cross-check the Planck and WMAP derived synchrotron maps and examine the accuracy of component separation pipelines used in these missions. So before going to the analysis, I would like to give a very brief overview of Minkowski functionals. So these are the morphological tools to study the statistics of a random field. And it is based on escalation set formalism. So on the right side, I have just kept some images to make you understand the escalation set formalism. So given a random field, we can divide it into binary field based on the thresholds. So what Minkowski functionals do is it probes the geometry of these connected regions and whole, which is the yellow region and the black region. So the main advantage is that it's a real space statistics, unlike the bispectrum, power spectrum, etc., which are done in Fourier space. Also, it contains the information of all the higher order correlations. So the speciality is that since we don't know the real nature of the synchrotron field or any other foreground field, unlike the CMB fields, so Minkowski functionals or these kind of morphological tools are more useful in understanding the statistics of foreground fields. So basically, we are using three scalar Minkowski functionals: area fraction, contour length, and genus. So this can be used to capture the non-Gaussianity of the random field. Now, we also use Kondo Minkowski tensor, which is one of the tensor Minkowski functional, which is a tensor analog of the contour length. So the speciality of Kondo Minkowski tensor is that it encodes the information of the anisotropy and alignment of the structure. You can see if given a structure, so this is computed from the tangent or the normal of the, which means that the direction information is there. So there is a parameter called alpha, which can give information about the anisotropy of the field. So alpha is obtained from the eigenvalues of the average W1 computed over multiple structures. So alpha is designed in such a way that if alpha is equal to 1, that means that the field is statistically isotropic. And if we have deviation from 1, that implies that the field is anisotropic. So given this brief overview, I'm going to the analysis part. So we start with Haslam. So the Haslam map obtained given by the Mathieu Remaze is here. So there are two steps we have done before doing the analysis. One is masking the field as done in most of the CMB analysis. So we use one parameter UCUT to mask the high emitting region. So we have used two, just for representation, I have used UCUT 60 and UCUT 25. So UCUT 25 means I'm removing more and more region from the central part. Also, we have used a bandpass filter, which is parameterized by LCUT, LC. So it captures the small scale features. So more LCAT means we are going more and more to small scale. So LCAT 30, you can see in the image that there are still some big structures in the field. But if we use LCAT equal to 20, which correspond to approximately 2 degrees, so there are only small structures with 2 degree size. So now I would like to discuss the results that we have obtained based on for the non-Gaussianity of the Haslam field. So on the right side, the plot is like this. So I have shown the V0, V1, and V2. These are the 3 scalar Minkowski functionals for the Haslam data as well as the Gaussian isotropic simulations. So the data is the diamond, and these lines are the obtained from simulation. So we can see that it's deviating from the Gaussian isotropic simulation, which implies that the field is non-Gaussian. So this is seen for both red colored ones and the blue colored ones. Just to remind you, red colored one is with less masking, that is the 60 Kelvin, and green colored one is more masking. Okay, so synchrotron field is non-Gaussian.
So you have 2 minutes, okay? 2 more minutes, yeah. Please.
Okay, I don't know, like I got only 4 minutes, ma'am, at that time.
Okay, go, please. Thank you.
Okay,
Go
okay,
ahead.
fine. Another important thing is that we found that more masking implies that the field is getting less non-Gaussian. So the amplitude, so what I am showing here is delta of V0, V1, and V2, which encodes the non-Gaussianity, the deviation from the Gaussianity. So for the green one, we can see that the amplitude is small, which means that if we remove more and more regions, central regions from the field, it's getting more and more Gaussian. Also, another very important thing is that we have found that if you go to small scales, parameters by this LCAT, we are finding that it's getting more, and this delta is getting more and more small, which means that if you go to smaller and smaller scales, the field is getting more and more Gaussian, which is supporting the previous studies. Another interesting thing that we have found is that it's about the shape that we found for these deltas. So there is a particular shape for all these 3 scalar Minkowski functional, which is equivalent to the Hermite polynomial H2, H3, and H4. So if you have a local type non-Gaussianity, which is commonly seen for inflationary non-Gaussianities, like the GNL kind of non-Gaussianity predicted by some of the inflationary multi-field models, so it is having this particular shape. So even for a synchrotron field, which has nothing to do with cosmology, we are finding some shape similar to this. So we found that this is some kind of kurtosis type of non-Gaussianity. We don't know the origin of this, but we found that, okay, this is a kurtosis type of non-Gaussianity, and that is very important if you are going to look for the kurtosis type of non-Gaussianity in the CMB experiments. So finally, we find that we fit a perturbation theory expression for this delta MF, and we find that it is working well for the cooler regions, which is corresponding to this 25 Kelvin green plots. Okay, here for the red, it is not matching, but for green, it is matching. Okay, quickly, I will go to the results that we have obtained for the statistical isotropy. So the major findings are that, so here on the right, I have shown the alpha as a function of the threshold. So this broader region is for the error bars from the Gaussian isotropic simulation, and these circles are for data. So for red one, which means that we are masking less, we find that it's deviating much from the Gaussian isotropic field. But for green, it is coming within 3 sigma, which means that if we move away from the galactic region, the field is getting more and more isotropic. Another important thing that we have found is that if you go to smaller and smaller scales, again with this delta alpha, we can see that if you go to smaller and smaller scales, the field is getting more and more isotropic. So once Haslam analysis is done, so we want to check what happened at the WMAP and Planck synchrotron maps. So we are expected to reproduce the same results from what we have found in Haslam, that will make sure that the WMAP and Planck component separation analysis is working well. So interestingly, we found that at small scales, the field is getting less non-Gaussian, because it's getting, you can see that V0, V1, and V2, they are getting more and more close to the Gaussian expectation. And another thing is that, so similar to what we have seen for the shape of this delta V0, delta V1, and delta V2, here also we are finding that it is having this H2, H3, H4 Hermite polynomial shape. So which again lead us to think that, okay, this could be from some source which can have this GNL kind of non-Gaussianity. Finally, we find that all the 3 maps, Haslam, WMAP, and Planck, their delta V0 are matching within 2 sigma, which implies that the component separation is working well, at least at the Minkowski functional level. And this is my last slide. So here, what we have done is we have just computed the Betty numbers, which are nothing but the topological quantity, but it is just the number of connected regions and holes in the exclusion set. So these two Betty numbers, we are finding that there is significant difference at the Betty number level. So Betty number, unlike the Minkowski functionals, mainly the first two Minkowski functionals, these are topological features. They are not the geometric features, they are the topological features. So at the topological level, it is mismatch, but at the morphological level, I mean, at least for V0 and V2, we found that, okay, there is match. So this indicates the importance of including topological features in the component separation techniques for the future CMB experiments. Okay, so this is a summary. So we find that overall level of non-Gaussianity decreases as more high emission regions are masked and as we go to smaller angular scales. And at the Haslam resolution, the level of non-Gaussianity is not low enough to model as Gaussian fluctuations, which is the standard procedure followed in CMB experiments. We found that there is a 3.3 sigma significance. And another important thing that we found is that the leading source of non-Gaussianity is the Curtis system, with the skewness being subdominant. And in the cooler regions, the non-Gaussian deviations agree well with the analytical expression. So these things are very important for modeling synchrotron emission. As the high emitting regions are masked and at small scales, we find that the Haslam field is interestingly isotropic. Finally, coming to the summary of the Planck and WMAP maps, we find that those maps are also showing similar features to Haslam map, which means that more Gaussian at small scales. The nature of non-Gaussianity is of Curtis type for WMAP and Planck synchrotron maps. Also, we found that all the maps match within 2 sigma for all the 3 scalar Minkowski functionals, which is a good news. Finally, the Betty numbers are still different for 3 maps, highlighting the importance of incorporating, there is a typo, topological features in the component separation. So thank you for listening. So open the question.
Thanks, Fazlu. One quick question from the audience before we close the session. Any question? Okay. If not, let's thank all this. There's one question from whom?
Yeah, there is one question.
Yeah. So somebody typed a question or?
One question about when you mask more and more regions, it tends to be Gaussian at small scales. Is it also dependent on different pointings in the unmasked regions of the sky, or have you looked at a specific pointing in that exercise?
So we tried different masks, so still we are getting that. So even though let's say that we are masking some 30% of the sky, so we use 2 different masks of 30%, still we are finding that. So which means it has nothing to do with the, and another thing is that most of the local features and filamentary structures are removed from the sky. So it is basically the diffused emission. So statistically we are seeing that this is still Gaussian. So
okay, thank you very much. So that was an offline question. I was asking for online, but let's end the session here today. And thanks to all the speakers and the audience. There was some technical problems. So from 6:30, the the WGG sessions are going to start. And I request everyone to be present there. I mean, just a request. Thank you very much. Thanks. So we end the session here.